This meeting is being recorded.
Good afternoon, everyone. I would like to welcome you to this webinar. My name is Charles Nyebeze, and I'm the Vice President, Business Development and Commercialization with the Center for Excellence in Mining Innovation. So in terms of just setting some ground rules for the webinar, you will be asked to please submit your questions to the webinar via the chat box. And after the 20-minute presentation, we will read out your questions, and Cameron can then proceed to answer those questions. At the conclusion of this webinar, we're going to send you all a link to the recording of the webinar, and we'll also be providing you with a copy of the PDF version of the presentation. So you can expect to get an email from us, within a few, maybe a day or two from the end of the webinar. Without any further ado, I'd like to welcome Cameron. Cameron, please come online.
All right, thank you, Charles. I appreciate the introduction, and thank you a lot for being able to put this together. This is the second webinar of a two-part series. The first one, we looked at introducing the core fundamental Electramet technology, and today's focus is following up to that, looking at two specific use cases, looking at recovery of copper from two different mining streams. So some quick high-level vision of what the company does. So we've developed this Electramet technology to selectively remove metals from a variety of water streams. So one aspect, we work with customers to remove these metals for discharge compliance, so meeting environmental regulations and permits. But we also are able to collect these metals in high purity and recover them in a variety of forms desirable to be recycled and sold back into the marketplace, thereby closing this circular economy. And given the nature of what we do, the type of water doesn't really matter. As long as there's a water stream with metals in it, Electramet is applicable. Wastewater, processed water, ingredient water, or mixtures thereof. And for today's talk, we're focusing on specifically some mining water streams. Now, where all have we seen Electramet successful? Here I highlighted in green, where we currently have active projects. Some are for recovery, some are purely just for environmental regulations. The ones highlighted in purple are tentative projects. We got some test cases done and working to get these systems installed. Highlight two out here in yellow, arsenic, selenium, because while we're able to remove them, it is more of a hybrid process that kind of takes some tweaks. Again, for today's talk, we're looking at use cases of removing copper from pretty complex water streams and then recovering it into a pure form. So looking at case number one, just diving right in, this is some mining water we received from a North American mine, and they tasked us with recovering some dilute amounts of copper, looking about 700 ppm, out of a very complex water stream. Their main concerns were the elevated concentrations of aluminum, manganese, and iron that was complicating their other recovery processes. So we used Electramet to very selectively remove just the copper, let everything else pass through, and then turn it into a pure form. So we had to do no other changes to the water. We treat it while acidic, let everything else pass through, remove the copper, and recover it. So we're doing a two-step process. Step one is treating this raw water through Electramet to remove the copper and trap the copper onto our Electramet cells. Then you get this copper-free effluent. Step two is now a switch in the batch, and I'll go into some drawings a little bit later to show this process. But then we essentially take all the copper removed that's in our system, and we push it off back into a dissolved state and concentrate it into a copper sulfate solution, which you can then process downstream. This example here, we took the copper out and purified into a high concentration copper sulfate stream, and then collected the copper via a cementation process. So this is more ideal situation if you do have this slight impurities and it's going to go to a smelter anyways, if you don't need cathode grade copper and just want to get bulk removal. And again, looking at this process, so it's a two-step process. We treat the water in a single pass. So this raw water goes through it. All the copper is trapped inside of our Electramet cell. Once we are saturated in copper, we will turn a valve. So we stop the processed water from going into our system, and we then do a batch mode with this, what we call a regen tank. And this is simply just a dilute sulfuric acid stream. When we choose this, so it's very nice at getting copper sulfate. It is well known how to process copper sulfate downstream into a variety of products. So as we do this, once this is done, we'll then flip another valve, close this orange stream off, and again, process more water. And the cycle is repeated over and over again until you have enough copper in this regen tank to be processed to your desired state. And what we're now starting to implement is, instead of doing cementation, we're now pairing with an electrowinning cell to retake the copper out of this complex stream, put it into a very high purity copper sulfate stream, which we then, under very controlled, mild conditions, will do an electrowinning process to produce cathode grade copper. And we match the rate of electrowinning here to match our rate of copper removal in our Electramet system, so we don't have to do very extreme power conditions. We're looking at still low voltage and low currents in this electrowinning process, whereas typically you're going to be in a more higher power regime. But given our design, we're not looking at removing massive amounts of copper in a short time frame. It's a slow and steady process, so the energy cost is minimal. We'll do this to get very high pure copper, starting with very low concentration of copper in this complex stream, and ending up with this pure cathode grade material. And the economics, for this case, are working out nicely. We're getting about 50% profitability based on the spot price of the copper. So there's some of the complexities and assumptions that we're not taking into account here, but in general, this gives you an idea of sort of where the economics are. And I'm going to go to a few slides down that really break down the economics even further. But now moving over to case number 2, and this one we're going to a little more details of the removal of the separations and really show you how it works. So here, it's not quite as complex a stream, where now you're getting less copper overall, but it's more matching the rest of the constituents. So overall, you're about 10% copper in this mixture that we then turn into, again, 99+% pure copper sulfate and then recover via electrowinning. So here now we're taking this raw water and passing it through our Electramet system. And with each pass we get more and more copper out. So here looking at a few hundred ppm delta in the first pass and then getting down to the low parts per billion in the second pass. So we have this tunability to, depending on the economics, remove however much you want. If you want low parts per billion copper, we can do that. If you don't want to go that low, it's fine. But the key takeaway here is the aluminum, the iron, the manganese. That concentration is not changing in this process. We are not removing these other metals in our process. So that means is these metals are not going to be trapped inside of our Electramet modules. So when we go to do this regen cycle, they don't bleed over. So here we're showing just a couple cycles where you start with about 400 ppm copper and doing this sort of switching process where you first remove the copper from the raw water, switch over to this regen via batch mode to concentrate the copper, and then back to treat more copper from the feed stream. So repeat this cycle over and over again. And every time you do, the amount of copper in this batch tank gets higher and higher. And once you hit this 5,000 plus ppm range, that is now where it is feasible to do efficient electrowinning to produce the high quality cathode grade copper materials. And you will notice that some iron and aluminum is minor contaminants. And this is because we are not optimizing the process. So this is bleed over from the feed water that is mixing with the regen tote. And this is a minor engineering challenge to solve to essentially flush out the feed water first before you start putting your regen tank over there. But at the end, it doesn't matter. These are low enough to not negatively impact our recovery process in the end. Just look at the high quality copper. And again, it's to show two different streams, different makes up different complexities, but getting roughly the same result and the same economics, roughly still about that 50% profitability of the recovered copper. And so now looking at how does the capital cost, the operational cost kind of fit in with this specific use case, and how does that scale from doing, say, a small system, which we see in some industrial effluent type companies versus maybe these larger mining applications where you're now treating millions of gallons per day. So because we are a modular-based system, each module can treat a set flow rate, handle a set amount of water per day, and you line these up in parallel to treat higher flow rates. So now, if you need to go from, say, 200 gallons per minute to 1,000, you just tack on more of these modules in parallel, much like you see with lithium-ion battery packs or fuel cells. And today we're seeing this blue line kind of curve with our current economics, our current size of manufacturing. And within 18 months, 2 years, we believe to have the capabilities and the infrastructure set up to get this cost reduction, to have a very, very capital cost efficient system. Okay. And then looking at more of a normalized basis, at the lower flow rates, the cost per gallon treated is going to be higher, but it does very quickly level out. Again, we have this modular system to where the cost per gallon treated is not increasing with size, but we do bottom out at a pretty decent level here on the 100, 200 dollars per GPM treated. But now what really matters is looking at sort of the operational cost, right? Because that's going to be the bulk of the cost for recovering these metals. And that's really what's going to dictate doing the solution versus not. So here I'm showing the copper and the orange, and want to kind of compare to two other metals that we've seen either in the mining industry or in some other industrial settings to give some comparisons of what dictates this cost. So the majority of the operational cost is going to be the lifetime of these modules. These are consumables. We use carbon-based electrodes, like batteries. Eventually, they will fail, and it's hours of use, not necessarily gallons treated. So, and the lifetime is based on what voltage we apply. The higher the voltage, the faster it's going to die. Lower the voltage, the longer it can live. And here's a prime example where manganese is about 75% of the voltage required, that is for copper, and copper is about 30% less voltage required than it is for nickel. So the type of metal doesn't matter. It's really the voltage that we have to apply to remove it from these streams. And we can see some pretty nice cost savings with scale. Again, because we have this nice modular system, it can really be optimized for these larger systems where the control panel, the PLC, all the automation scales up very nicely. So all you're doing is adding on more of these modules, which fit in very nicely into shipping containers for remote locations. Requires very low power. So also suitable for remote locations. And I'll dive into that in just a little bit. Again, looking at the sort of contributions of what dictates these costs. So from the OpEx side, that's been the main piece. That's how we really sell these. The energy cost is very minimal. It's usually less than an LED light bulb. We're doing low voltage, low currents. The pump is going to be the bulk of the energy cost, which I do not include here. This is just the energy cost to do our separations, to remove the copper from the water. The labor is also very minimal. It's well suited for remote locations. It's a fully automated system. You can access it remotely via 4G, Wi-Fi, LTE, Ethernet, whatever system you use. The replacement is simple. These are like replacing a fridge filter, a quarter turn. It takes about 15 seconds to pop one of these cells out and put a new one in. And that can be disposed of as non-hazardous landfill or sent back to us for recycling. Now, the bulk of the cost of that is this cartridge replacement. Given our operation, you're looking at a few months of life. You can go a little bit longer depending on the metal you use, maybe a little less if you push to more harsh conditions. But that is the bulk of the OpEx cost. So optimizing the operation to extend the lifetime of these cartridges is how we get the best OpEx. Now, the CapEx is mainly built into these docking plates. It's what the cartridges tie into. That's how we connect the power. That's how we connect the water in and out. And that's how we really tie it all together. The control panel, PLC, the skid, those are all very low-cost systems, look very efficient. Not a lot of room for cost savings in the future there, but mainly on all these docking plates, which have a high potential to do cost reductions with economies of scale. And then really diving into it, the way we're set up is we do have two options for the business model. We do see some customers like to do a capital purchase, much like you see with ahorro membranes. You buy the system, and then you buy the consumables as you need them. This is not our ideal scenario, but we do offer it because some customers like it. What we prefer to offer is more of a water as a service. So we can lease the capital equipment. There's zero capital cost put down for this. And then you sign a 3-year contract. And with that contract, we provide all the consumables as needed. You get the remote access, all the remote monitoring and service required to make sure the system is running as desired for the life of the contract. And what this does is it really now takes rid of the upfront capital investment. And for those looking at discharge compliance, it is immediate OpEx savings, but also looking at the resource recovery, if you are not recovering the metals, right, you're not paying for it. So if we buy something capital purchase, it takes time to get the ROI. Here it's going to be instantaneous ROI as we recover this copper to then sell. And the main benefit is now you have very predictable costs. You don't have massive spikes for buying capital purchases and having to amortize it over the years. So this is the model we strongly prefer, but we do not shy away from these other capital purchases and purchasing consumable models. Each customer does things differently, and so we're flexible enough to kind of tie into how they operate. All right, so now I want to switch over these last few minutes here and kind of run you through what our remote system looks like, and this is what you'll be seeing if you're running one of these systems. So for each application, we will design a specific sort of PID that fits your process. And we track things like pressure drop across filters, pressure drop across our Electramet modules, the current, the voltage, the power, the flow rate. So all of these parameters you can know and make sure your system is working as intended and start to preemptively see if there's any signs that are off scale that might need maintenance. So then going through, looking at, say, looking settings, right, we have security access depending on who you want accessing it to do what, such as change the voltage, which targets different metals, how fast do you want to record the data, okay? And then looking at all the bypasses, to bypass the system, to turn different pumps on, change valving to control where the flow goes. So now the owner, the user, can set controls of who can do what in this system, so you don't have the wrong person pushing buttons and doing something that hurts the end system. You can go over here and click on the modules. So if you have one or more, you can see each one individually, sort of what volt it's running at, how much current you're seeing, what's the total power, and you can add it up total with all of these different modules. So you can see if there's one's a problem or one's not, and they're all working properly or not. So it gives you very fine-tuned control of the system. So then moving on to looking at some stats, you can look at, how much water you're treating, how many hours has it been used. Like I said, hours is a better predictor of lifetime versus volume treated, because we're not like a standard filter that's going to absorb materials and clog. It's more like a battery or capacitor. That's hours of applied voltage that's going to dictate when it's dead and when it's to be replaced. Now, from looking at some charts, you can see we can track things like flow rate, your module voltage in real time to see if things are, again, being as they should. And if you start seeing variances from what it should be, something's going wrong, we can fix it. Again, the key tell is current, right? Much like a battery, if current gets slow, you're not doing any work. If current goes way too high off the charts, something's inefficient is happening. So we can tell a lot just from voltage and current to know that these systems are running as intended. And our typical way of working with customers is for these new types of water streams, we like to get a sample, do some feasibility testing in-house. And what this does for us is taking a small snapshot of like 5 gallons, and we build a process to be able to treat it. So it says what voltage do we need, what flow rates, what residence times required per cartridge to be able to meet the customer's targets, whether it be recovery or discharge or both. And this is the basis for proposal to do some on-site piloting. So now we lease one of our small demo units. This is like the size of a standard home water softener, 4 feet by 5 feet. You can handle 2 cartridges, so we can do up to 20 gallons per minute. And we let this run for 1 to 2 months. This is now enough time to be able to predict the lifetime and failure rates of these modules, of these cartridges. But more importantly, it lets us get real data on the changing feed water, because what you see one day is not always the same from day to day. So you might have spikes in copper, you might have spikes of impurities. So we are able to then tune the system all through automation so it can match the incoming water stream. Then from here, we would now get a really good picture of what the OpEx is. And that is our preferred model. We can then build a proposal for a full-scale system based on the OpEx, or we know the size of the system, what that CapEx will be. And because we have a good predictor now of the consumption rate of these Electramet cartridges, we can then be very high predictability of deciding, how often does it need to be replaced? Is it a 2-month cycle, 3-month cycle? Will it last less, last more? All that will be determined on site with a few months of testing. And then from here is the standard full-scale installation. Sign the contract, purchase the system, for model is up to the customer, and go. All right, so with that, I would like to thank everybody for their attention, and we'll be happy to begin answering some questions.
All right, thank you, Cameron, for the presentation. One of the questions I have here is, how do you deal with suspended solids?
Mm-hmm. So we are a very good particle filter. We're also a very expensive particle filter. So we like to have very low TSS coming into our system. It's more of a size of particle versus a concentration ppm of particles. We've seen typically between a 1 micron to 5 micron filtration up front is enough. If you're less than 1 micron, as long as it's not super sticky, it will just pass through our electrodes. Our carbon electrodes are very macroporous type cloths. But eventually, if one clogs and sticks, and then it's going to be a cascading effect to clog it up. So we do need very good TSS control up front.
Okay. All right, thank you for that. Another question we have here is, do you form copper metal or copper oxide at the Electramet unit?
We can do a little bit of both, but the main form is going to be copper metal on our cathode. Depending on the pH of the water and the cell we use, we might make copper oxide. Say, for example, it's not acidic. If we're like pH 5, then we can form more copper oxide on our anode, or even some copper oxide on our cathode. It'd be copper 1 oxide versus a copper 2 oxide. But the majority of the removal, the form of copper is going to be copper 0 metal on our cathode.
Okay. Thank you for that. Another question here is there a particular chemical species of copper that gets selected, or is it any ionic form?
Pretty much any ionic form. Copper 1, copper 2, even if it's chelated copper, not an issue. We've done lots of work with things like antiscalants, antiphthalates, looking at RO brines, cyanide. None of that really matters. It might change the operating voltage slightly, but it doesn't matter. As long as it's ionic, dissolved, like dissolved metals. If it's particulate copper, we can probably filter it out, but then we're just being a particle filter, and there's probably other solutions than what we can do.
Another question I have here is, how do you deal with samples that are coming from offshore, like maybe off country? And specific here is sampling from South America. Mm-hmm. How would you deal with a 5-gallon sample coming through from South America? And is there anything you want to give as advice for somebody who's packaging a sample that's coming from offshore?
We haven't had any problems with that. We've had samples come from Israel. We've had some from South America, from Canada, from Europe. That's going to be, I think, more dependent on the specific rules of those countries and what they can ship out. Okay. We typically have UN compliant jugs that have proper labeling, at least internal in the U.S. Department of Transportation shipping. We haven't had any issues with our imports. As long as we're known ahead of time, we can set up the import-export. People take care of it. It's just a matter of time. So most of it isn't hazardous. It is small samples. There's lots of, I guess, sort of loopholes to get around all of the paper trails.
Perfect. Okay. Another question here is, are there problems with scaling up of the electrodes?
Surprisingly, none. Like if we get hardness scaling, because we use all carbon-based electrodes, the anode will produce small amounts of acid. So if there is any scale formation, it gets redissolved. Also, with these copper waters, we're at very low pH. So if you're at pH, 0.5 to 3, you really can't form hardness scale. It's going to redissolve. You can't have carbonates. It's all going to be released as CO2 that low. Because of the electrical field plus the pH modification we can do, we have had some pretty extreme conditions and not seen any scaling form. We've had up to 70 grain of hardness, still no scale formation. We have not looked at other types of scale formation, such as barium, etc. But we've only had low concentrations of waters that had those constituents. But I still don't see it as a problem given the way our system works with the electric field, the pH modulations, and the carbon-based electrodes.
The question here is a follow-up to the copper metal question. Does the copper metal collect from the cathode side continuously?
Yes and no. So yes, as we are running, the copper will collect on the cathode side as copper metal. Eventually, because the electrode is our water flow path, if we collect too much copper, we will start to see a big pressure drop. And that is when we have to do this regen cycle to get the copper off of our carbon so that you don't see a massive pressure drop and then you can remove more copper. Because at that point, the electrode's still good. We can do more work. We don't want to stop it, take it off, and pull it apart and then collect the copper. We can still utilize those carbon electrodes. Right, we're looking at, depending on the concentration, right? If we're in the grams per liter, it's going to saturate very quickly. If we're in the tens to hundreds of ppm, we're above 80% cycle time of cleaning and removing the copper versus doing the regen. The regen takes 5 to 15 minutes max, depending on how pure we want that end stream to be. How much do we need to not have the feed water mixed with our pure copper sulfate stream?
Okay, thank you. Another question we have here is what kind of modifications are needed for AS removal?
Yes, for arsenic and for selenium, what we focus on is making sure the arsenate and selenates are reduced into the nites form. So arsenite and selenite. Then those are more easily removed with a iron-based precipitation. So we could produce some iron. It is a 2-cartridge system where one, we could produce the iron, probably as an iron 2, which will help with reduction as well. And then second one is to get everything in the proper state to be removed with an iron coagulation. We have some good success doing this in some smelting companies, but that's usually looking at high ppms down to a ppm or so, not looking at getting the parts per billion ranges. So we just enhance the traditional iron coagulation-based process. So the combined system tends to be a little bit lower cost, less sludge overall, more automation. But a complete Electramet system for arsenic stun removal is not ideal. We can do it, but that's going to be more costly than doing this hybrid Electramet coagulation-based process.
Thank you for that. Another question we have here, and I think maybe this will be our last question, is just what kind of scale can you build this system up to?
It's modular, so we could go as large as you want. Currently, most of our industrial customers are in this, tens of thousands to a couple 100,000 gallons per day treatment. We got a few applications looking at the 1 million gallons per day. We got one mine in particular in Australia that we're starting to pilot for an 11,000 gallons per minute system. So really now we're looking at a handful of shipping containers. But because it's modular, it's really easy to keep adding on more modules to meet the needs. The complications, the challenges arise because the economics, we scale linearly. If you're trying to do, say, some kind of discharge compliance, when you're at scale, dumping in chemicals, much better if you get, depending on what you want to do, the economics start to change. And the threshold is in this 1 to 3 million gallons per day is where the economics begin to get muddied, depending on what the customer actually wants to do. For recovery, we maintain better advantage. For purely discharge compliance, that gap in cost savings is reduced.
Okay, thank you for that answer, Cameron. And Cameron, seeing that we have reached the end of our presentation, I'd like to thank you for giving us this presentation. And I was going to ask you maybe to say a few parting words to our audience.
No, thank you for the time. This is and especially to Semi put this together. It's really exciting to get Electramet in front of this crowd of these types of people, and really the feedback we've already seen from the last webinar of applications and thoughts we never even begun to imagine as we learn more about this marketplace. And I'm really excited to hear back from all the audience members today, and hopefully we can work together in the future.
Okay, thank you very much. So to our audience, again, thank you for joining us. You will receive in your email a link to this video and also copies of this presentation. We will also give you in writing some answers to the questions that we asked here, so that you can have those for your reference. Thank you again, and we look forward to you joining us on our next webinar. Thank you. Bye-bye now. Thank you, Cameron.
Thanks a lot, everybody.